Good afternoon. This is David Eastwood, Geotech Engineering and Testing. Welcome to our presentation today on geoforensic study of exclusive furniture building. That's in Houston. It's a big furniture store actually in Rosenberg. And this thing has had some problems, foundation problems. So we were hired to go get out there and look at it. We got about 100 people plus RSVP for this presentation, mostly engineers. My contact information is David Eastwood, de@geotecheng.com. My phone number is 713-699-4000. And of course, this presentation is going to be on YouTube. So you can watch it on YouTube at any time you want to. Geotech Engineering and Testing is in Houston. We've been in business for about 38 years. We do geotechnical and environmental material testing and geoforensic engineering. We got about 60 people, engineers, geologists, technicians, support staff, and we work all over Texas, Louisiana, Oklahoma, and New Mexico. And we have our own rigs and equipment and accredited laboratories. So we're a full service company. If you have any questions, please type in your questions in the Q&A section of this Zoom meeting. Exterior of the building. Basically, this is what the building looked like when we were out there in February 13th of 2018. It's a nice building out there in Rosenberg, Richmond, Rosenberg area. It's kind of like the front of the building. A lot of landscaping around the building. This is, again, the front. This is the front of the building. You go to the sides of the building, parts of the sides of the building, got landscaping, lots of mulch. Everything is domed up and basically dammed up against the building. They got sprinkler systems on the sides where they have landscaping. Parts of it, of course, is grass in here. This is the back of the building on the north side. Real negative drainage in here in this area. Water just going out there towards the north of the building, low area. This is on this west side of the building is a concrete tilt wall panel. Of course, the building is a one-story tilt wall panel structure with concrete paving here on the west side, and you can see a truck well there. The gutters are going on to underground drainage system. Interior of the building is a lot of furniture, and that's what it looks like. This is kind of like the warehouse out there where they put the furniture together. So project timeline, site visit, review of the available documents, field exploration, results of laboratory tests, engineering analysis, reasons for distress, repair recommendations, and additional studies. That was kind of like our overall goal of the projects, that how we approached it. Project timeline in 2013, somebody did a geotechnical report. We never got a copy of it. 2014, the building was designed by a structural engineer. 2015, they finished the construction in June of 2015. And around 2017, the cracks start showing up. And then 2017, the structural engineer went out there, started looking at it. Then in 2018, we were hired to kind of look at it and figure out what's going on. Site visit, distress outside the building. These points 1, 2, 3, 4, 5, all talk about distress locations around the building. And lots of cracks out there in the exterior. These concrete kind of panels are coming off. Landscaping, of course, is real bad. Of course, you have a domed up mulch around the building where they have landscaping with a sprinkler system. Some areas they had bed liners. They had some area drains out there, and some of these area drains were above the grade, so water could not get into it. They had sprinkler system on the south side and on the east side of the building. No sprinkler system on the back side of the building, which is the north or west side of the building. That, of course, when you have moisture conditions that are kind of different on each side of the building, it causes movement, especially in the area like this in Richmond, Rosenberg area, where you got a lot of highly expansive soils. More cracks out there in the exterior sprinkler system. They had some drains in here that kind of what drain into a underground drainage system here. There's some gutter looking things. More sprinkler systems. This is the picture, kind of like on the east side of the building. You can see all the landscaping. You got the bed liners in here, holding the basically water next to the foundation. More bed liners in here. Aerial area drains in here. You can see sitting up pretty high. Domed up landscaping. Negative drainage next to the foundation. More of this crack type stuff. Paneling's coming up. Cracks in the brick. From the crack kind of concrete block fascia, and the brick is all separating here. Cracks in the floor slab areas. And this is the back of the building, and you can see the drainage is really bad. You go out there, dig a hole right next to it, you will see water, kind of perch water table out there next to the concrete tail wall panel. More separation of this concrete block facade. Again, negative drainage you can see out there on the north side, the back of the building. Look at the joints on the tail wall panels. They were pretty stable. We did not see any movement of the concrete panels. On the west side, you can see the gutters kind of draining into an underground drainage system. More gutters, some landscaping in here, small trees. Again, this is the west side of the building. You got planter areas here, a truck well here, sprinkler system. Lots of cracks out there in the truck well area. This is the west side again. You can see the tilt wall panels. At the time we were there was no cracks out there in the tilt wall panels. Everything was pretty stable. If the panels, have movements, that would be a typical picture of a tilt wall panel movement. This is not, from the site. This is just kind of showing you what the tilt wall panel looks like when it kind of starts moving. None of this was on this project, so there's no movement on this project. There's distress inside the building. When you go inside the building, these are the observation points inside the building that shows the distressed areas. Some cracks out in the tiles. Separations in here from, I guess, the expansion joints in the slab. Separating. Lots of sheetrock cracks. More floor slab separations in the joints. More slab separation in the joints. Sheetrock crack. Sheetrock crack. More sheetrock cracks. More sheetrock cracks. More cracks. More cracks. Floor slab cracks. We got a lot of these shrinkage crack looking stuff in there. Separations here. more separations between the staircase and steel frame for the second story. There was a separation there, moving. Again, you get separations here. Staircase going upstairs. Some of the ceiling tiles that are coming up, moving. Cracks in the tiles out there in the stairs. So we started reviewing the documents, and this thing always was designed and built. This is a 236-foot wide by 200-foot long building, and it's sitting on drill piers, of course. You got tilt wall panels on it. And looking at these piers, some of them are about, just a typical pier again, 12 foot below natural grade. That was the depth of the pier. Typical size, 24-inch, 30-inch drill shafts, 32-inch drill shafts, and 48-inch with a bell. The floor slab was 5 inches thick, and it had steel in it. This is the drill pier coming in down into the grade beam. The floor slab was 5-inch concrete slab on 10 mil poly on 2-inch maximum sand fill. The floor slab should have been reinforced with number 4 bar at 18-inch spacing, 5 inches thick. The steel was supposed to be at 2.5 inches below into the concrete. Concrete should have been 4,000 psi, 28 days concrete. So it's not bad. 4,000 psi concrete, 5-inch slab. Water bills. We look at the water bills, and in or about near the 2018 or so, they had a lot of water bills. They had a leak. They used a lot of water out there in January of 2018. Before then, it usually was about, 17,000 gallons or something like that, or 34 gallons. But also in the water in 2018 jumped to about 68,000 gallons. Went out there, did some field exploration. That included doing soil investigation, doing some GPR, ground penetrating radar. We put in piezometers. We did micro elevations. We did test pit excavations. We also did drill footing exposure. So here's what it looks like. These are the borings. We did the interior of the building, B8, B4, B5, B6. We put piezometers at B4 and B5 and B8. In the exterior, we did borings B1, B2, B3. And then we did test pits. Right here, test pit 1, test pit 2, and test pit 4. This is 2 here. And so we exposed the drill piers in the back on the north side, DF1 and DF2. That kind of gives you the overall of what we're looking at. The exterior borings, we did with our drill rig, went out there, did borings to a depth of 25 feet to see what kind of a soil we have out there. Well, we expected highly expansive soils, which that's what we found out there when we did the borings out there. Really highly expansive soils. Some of these soils really gumbo clays. Checking the strength with a hand penetrometer, looking for root fibers to determine the depth of active zone. As you go deeper, you get lower root fibers. Root fiber extend to an area where there's oxygen and water. When there's no water or oxygen, they start dying. That indicates the depth of active zone, the depth that soil experience shrink and swell. So it's very important when we do investigation to look for root fibers. In all of our geotechnical reports, we show root fibers to indicate the depth of active zone and movement. We also did some GPR on this place. GPR uses an antenna that transmits electromagnetic energy similar to the one cell phone use. A receiver also located in the antenna and receives the reflected signal, and then so from that, and when it encounters with the soils with two different dielectric values. So using that, we can tell if there's any underground utilities or voids under the slab. We did the GPR in 4 locations throughout the floor slab areas. We also checked it for void and moisture. This is a typical GPR area that used to see if there's any underground utilities, voids, high moisture areas. It's a typical screen you get. Somebody got to interpret that. That's the GPR. You run it out there on the floor slabs, trying to find where the steel is. This is where the concrete core was. Again, checking out there, trying to find steel location. And also the depth of the steel. These are boring locations. These are the steel locations. Try to do the borings where there's no steel there. Again, more GPR. But also we did floor slab coring to get core samples of the concrete to see how strong it is, and also do our borings out there. So we cored that slab at several locations. These were like, I think, 6-inch cores, 5-inch cores, something like that. And yeah, these are typical cores. Then we did interior borings. We use our portable rig out there and just start drilling out there to see what kind of a soil we're going to get out there. And of course, it was all highly expansive soils. We'll also put piezometers. Piezometer, we're trying to figure out if there's water under the slab or next to the foundations. These are piezometer locations, 1 outside and 3 inside, just to see if there's water under the slab. It's basically a 2-inch PVC pipe out there, and you got a 10-foot screen. Okay, these are about 20 foot deep, 10-foot screen. 0 to 10 is PVC pipe, and then below that is a screen PVC. And then you put sand around it and put bentonite balls all the way to the surface above that. These are the exterior typical piezometer. That's what it looks like. PVC pipe. These are perforated. Water can flow through it like that. So the piezometer I think here we use, I think it was 1-inch piezometer. And we drill the hole and put the piezometer in there, put sand around it. And usually we're putting sand around the piezometer and put bentonite chips, and then at the top, we grouted it, make sure no surface water gets into it. And then we measure the depth of the water. Interior piezometers, typical piezometer, PVC pipe, drill a hole first, and put the piezometer in, put sand around it, put bentonite balls, chips around it. These are the bentonite. These are mineralite type soils that expand, doesn't let water to come in. So that we don't measure surface water. We want to measure the groundwater. This is a piezometer. We put a cap on it. That's what it looks like. Here's when we're putting sand around it. That's a typical cap with a piezometer. Like that. So the piezometer consists of a PVC pipe. You put sand around it, then you have bentonite seal, then you grout it all the way to the top. And that's the stand, kind of the pipe that gets out of the ground, or you put a cap on it in here. You measure the water level. You go out there and start putting tape measure in the piezometers and measure the water levels. We measure the water levels in these piezometers at various depths, and none of the piezometers showed any water. So it was totally dry inside and outside of the building. We didn't hit any water within the top 20 feet. The PZ1, PZ2, PZ1 outside was 20-foot depth. It was dry when we tested it in 2018, February and March. Piezometer 2 and 3, they were 10-foot deep inside the building. We measured it 2 times, February and March. No water inside the building. So there was no water underneath the slab here on this project. We did have some perch water table on the north side. We did also elevations of the floor slabs, basically to see what the elevations looks like. Use a zip level technique to use the water levels. It's a typical, zip level device that you put it on the floor slabs, and you can read the elevations on it. So the typical zip level system. These are the elevations that we got. The kind of interior of the building, we had some bowl shaped looking thing that minus 0.5, and the outside on the north side, it was 2. So we had a total differential of about 2.5 inches. We had a leak in this part of the building out here outside. And then we had a water leak that, this is the fire water heat line that was leaking. So that's what the kind of micro elevations look like, kind of like north of the building, and the kind of east and west, kind of the area that's brown was kind of heaving. We did test pits at 4 locations. Test pit number 1, test pit number 2, test pit number 3, test pit number 4, and 4 locations to see what kind of a grade beam, really connections the tit wall has out there. What does it look like? This is the tit wall panel on the north side, and if you excavate, you see water coming in. So that's test pit number 1. Test pit number 2, they had water in it too. Test pit number 3 was dry. Test pit number 4 was dry. There was no water. We backfill everything after we dig it. We compacted it. That's what it looks like. So test pit number 1 on the north side, we had 0 to 5 inches lean clay. Below that, we had lean clay to 30 inches. Tail wall panel thickness was 8 inches below grade. 18 inches that we measured, 3 inches above grade and 15 inches below grade. Panel width was 9 inches. The design was 8 inches. Tilt wall panel total depth was 18 inches below grade, which was matched to design. And we saw basically in test pit number 1, we observed number 1 and 24 hours later, and we found water in it. This is test pit number 2, 0 to 5 inches lean clay, 5 to 30 inches lean clay. Again, 18 inches, kind of like the depth below grade kind of stuff. Panel was about 8.5 inches. And the panel was supposed to be 8 inches. And we found water here. Test pit number 3, we didn't find any water. And it was the same concept, tail wall panel was 9.5 inches wide. In this case, Design was 8 inches. Design was 18 inches for the panel should be below grade, and it was 18 inches. Test bit number 4, it was dry, and the same thing. Lean clay, had a little bit of fill, and it was fine. Now we started exposing drill piers, drill pier number 1, DF1 and DF2, see what kind of piers are underneath these tilt wall panels. This is a pier grade beam connection, or really not grade beam, pier to tilt wall panel connection, and there was no separation. Tilt wall panel was sitting directly on top of the piers, so there was no separation there. We measured the pier size, and we also measured the depth of the pier. And to see what this is the pier here, we measured the depth and find out where the tip of the bell is, and measured it from the shaft to see what size bell we have. So we found out for DF1, the diameter shaft was 32 inches. Design was 32 inches. Actually, we measured at 38.5 inches. The design bell is 78 inches. We actually measured it as 87 inches. The depth of the pier was supposed to be 12 feet. We measured 12 feet. Going to DF2, the location, it was 30 inches in diameter, and we measured 32 inches. Bell size design was 78 inches. We measured 83 inches. And the depth was 12 feet, which met. So the piers were all installed properly. These are DF1 excavations again. Shaft 38.5 inches, 12-foot depth. It met all the design. Comments on pier connections. The connections of pier to wall was generally good, without any gaps, which means that the panels are not separating from the piers. When we went out there, the panels were not moving. Test the DF2 in here again, 12-foot deep. The connections between the pier and tilt wall was good. Bell size was 78 inches for design. Shaft was 32. We measured 83 and 32 inches, which all match. Laboratory testing with the Atterberg limits, classification tests, sold strings, proctor tests, well tests, concrete compression tests, and measured soil suction, and one-dimensional swell tests. This is soil stratigraphy. B1, B2, and 3. B3 were drilled outside the building. It's all fat clay outside the building. Inside the building, we had supposedly select fill below fat clay. But the select fill had a lot of gumbo in it, a lot of expansive soil in it. So they didn't do a good job of quality control to make sure they have select fill underneath the floor slabs. Some of these soils had PIs of 28. A typical select fill should have a PI between 12 and 20. So they put expansive soils underneath the floor slabs because of poor quality control. So we found 0 to 8 feet lean clay, 0 to 25 fat clay, 18 to 23 lean clay. So fat clay, of course, gumbo. The PIs of the soils were 30 to 70. So from 33 to 70, it's a highly expansive soils underneath the floor slabs. Boring logs, the boring outside B1 was outside. Fat clay all the way down. Look at the PI, 48, 78, 70, 67. Outside again, 59, 65, 33, 64. These are B3, the outside boring. Fill inside building, we had fill up to 8 feet. The fill had PIs of 28, 29, not good. You don't put a 29 fill PI underneath the floor slabs. That defeats the whole purpose. This one had 6 foot of fill, lean clay. PI is 25, 25, 27. No, not good. None of these meet specs. Okay. This one has a 6 foot fill and a PI of 16, which is good. This one's got PIs of 25 and 19 and about 7 foot of fill, lean clay. That's the interior building. B8 interior building, 6 foot of fill, PI of 19. So if you look at these boring logs, you got PIs all the way to 29 underneath the floor slabs. Some of them are meet select fill, some of them don't. We run a proctor test to evaluate the compaction of the fill under the floor slab. A typical proctor for the soil was PI of 28, liquid limit of 46, maximum dry density of 107 and 17%. We compared the compaction of the field soils to the proctor that we ran, and all the compaction passed. They compact the soil properly, but they put the wrong fill underneath the floor slabs. We also checked the concrete. We capped these concrete cores that we did for the project. We put them in a compression machine. We put load on them and broke them. That's a typical core after we kind of tested it. We measured 5,000, 46,000, 4,600, 3,500, and 5,300. Design was 4,000. So essentially, the compression compression test for the project passed to have good concrete on the floor slabs. Soil suction test. We ran some suction tests on some of the soils, 2 of the borings. Suction is referred to as a free energy in the soil and water. Soil suction may be described as ability of an unsaturated soil to attract retained water. So we use a system called WP4 that we have. It measures the soil suction. You put the soil sample in here. It reads the suction for you. So these are the borings, and you put them in the soil samples in here, and it reads the soil suction. Looking at the soil suction, this is a soil suction boring B7, and this is B1. So B7 is the interior of the building, and B1 is the exterior of the building. Measuring soil suction, we measured somewhere about 3.4, 3.5, and they come over here. Then B7 inside the building, the soil suction dropped to about 2.8 or so. That means the soil was really high moisture. So if you look at the moisture in the soil as a function of depth, this is an outside boring. B1, kind of high moisture, you can see. Really high moisture in B1. But boring B7 was really dry. So that was a moisture difference between B1 that's outside and the B7 that's inside that was kind of dry. Same as shows that with the soil suction that shows B1 had an equilibrium suction of about 3.4 pf, but it was dry and really wet. B7 from basically near 5 foot or so had the soil suction that was 2.5. That means the soil was wet. Swell tests. We also ran some swell tests here, and basically you put a soil sample in here, and you load up to a geostatic stress, which is a load of the soil on top, load that's on top of the soil. So if the soil is 10 foot deep, it's got about 1,200 PSF loading on it. So if you get a 10-foot depth soil sample, you put 1,200 PSF on it and add water and let it swell. You know, basically what you do is you take a soil sample and you add water to it and let it swell. Then you add load to it to get to the initial void ratio. This is called swell pressure. At this level is a swell pressure. So you get basically, this is a swell test apparatus. That's what it looks like. You get a soil sample, you cut it, and you put it in this ring like that. You put the soil sample in this cell. You put it in this machine. This measures the swell. You add water to it. And you measure the swell after you add water to it. And you take the moisture, so the sample, you weigh it, you dry it up. That's what the soil sample looks like. Again, you get a soil sample, you add water to it, you let it swell, then you add load on it, and it gets to what's called swell pressure at the same vertical strain or void ratio. That's how you run the soil swell test. Potential vertical rise. We measure the PVR for this site. PVR is an index property of soil. Basically, it tells us how much heat we can expect at a specific location. When we look at the aerial photo for this site, there was no trees there. So instead of using TxDOT-124E for estimating PVR, we use AASHTO method. You use AASHTO method for PVR calculation. It gives you a lower PVR because it assumes percent swell is linear from top to a depth of the bottom of the active zone. In this case, the movement active zone was 10 feet. So we assumed a linear. Maximum swell pressure near the top, and it reduced as you get to a depth of 10 feet. There was no tree there. If there was tree there, then you have to use TxDOT-124E, and in that case, if you use TxDOT-124E, that shows percent swell constant with depth. That gives you a higher PVR value. So we ran the PVR, and here for PVR, it was 1.6 inches for basically soils with the PI of 40. And this is the natural dry conditions. And this is the kind of come over here to a depth of active zone of 10 feet. It gives you 1.6 inches PVR. Okay, so that's PI of 40. Now, if you got a soil with a different PVR, for example, this one PVR, soil PVR is about 40 and is about 3.7 inches. That's the PVR for the soil, assuming a total dry condition in the exterior boring. So that's what it looks like, 3.7 inches PVR. Engineering analysis, we reviewed aerial photos, review of topographic map. We looked at the water leak and water usage, tree survey, macro elevation, on-site field compaction evaluation, perch water table evaluation. We look at the soil moisture profile, soil suction, liquidity index, soil pressure, uplift capacity of drill piers, rainfall, ground penetrating data, and concrete strength floor slabs. Aerial photo, if you look at the site in 2011, there were just grass and weeds in here. Then they started building the building in 2015 or so. This is where the building is. When you look at the topo map, it shows a detention pond near the building. We didn't see that out there in any of the aerial photos, but the topo map showed the detention pond there. Somebody backfilled it, maybe, I don't know. Water leak, when we checking out the borings and doing the testing out there, we found out there was a fire line, fire water basically lining here, and it was leaking at this location. So it was excavated and found a pipe that was leaking, and it was fixed. Tree survey, we look at the planter areas around the building. There are trees around the building. What these trees are too small to cause any problems. These are little bitty trees. So we discounted the affected trees around the building. Elevation. We look at the elevations of the building. This is tilt. Basically, it's called Y over X. When the whole floor slab is rigid and moves uniformly, it's called tilt. Basically, tilt is a planar rotation measured over the length or width of the foundation. So if you got a building, a floor slab like this, and you get elevations on it, if the lines look like this, all uniform, that's tilting. Just says definition of some terms here. Deformation is a change of shape of foundation from the original foundation construction. Deflection is the maximum deviation from a straight line between 2 points. Deflection ratio is basically deflection divided by the horizontal distance over which it occurs. They call it also slope. So if you look at the deflection between 1 and 3, 1, 2, and 3, this is the deflection. This is not the deflection here. This is wrong. So you don't use that as the deflection. This is what you assume as your deflection. PTI has got a guideline for evaluation of the elevations on a slab-on-grade. It's a good document that was helped by the Houston FPA and PTI. We have a concept called L over 360. We say we should not have deflection of more than 1 inch in 30 feet. So that's the allowable deflection for floor slabs. So looking at the elevations of the slab with the exclusive furniture, we ran 2 sections, section AA and section BB, all the way here on the floor slab to see what the elevations look like. This is section AA, and you can see going up and then going down, and these are 0 elevation here. Then it jumps to about 1.7. This is section elevation BB. Starts over here, this section, goes down from 0, then goes up again. So you can see all the slab moving, from 0 to about 200 something feet, 300 feet. Again, you run the elevation test and you get the allowables. This is the actual deflection, L over 590. Tilt was 0.02%. It passes. In here, section, this is BB. And if you look at this one here, it just goes like this. And you got the actual is L over 339,270 and tilts up 0.7%. That means all the elevations pass. So all the movements for the floor slabs for this project are within tolerance. Everything passes. AA and BB, actual L over 590, allowable, they all pass. These are TRCC, Texas Residential Construction Commission, some of the tolerances they have for structures on residential structures. I just thought that one would be kind of something you want to look at. Floor slab crack should not be more than 1/8 of an inch. Flat work size, 1/4 of an inch. Flat work separation in expansion joints, 1 inches. Stairs should not have more than 3/8 of an inch settlement. Carport, garage cracks, 3/16. Sheetrock, 1/32. Brick, 1/8. Joint gaps in the brick, no more than 0.25 inches. Compaction. Again, we ran the proctors on the project, and based on running a proctor and checking all the densities meet project specifications. That was the proctor on the project, 107 and 17, maximum dry density 107, water content of 17%. The compaction was 95 to 100%. Everything was compacted, but they put gumbo clay underneath the floor slabs. Perch water table. The piezometers were all dry, so we didn't have to worry about water like that. But some areas near the tit wall panel on the north side, you dig a hole, got filled up with water. That was perch water table with that, but there was no actual groundwater under the floor slab. These were the perch water tables we found on the north side of the building. Soil moisture profiles, looking at the soils out there, B1, B2, B3. These are the exterior borings. The moistures were near the 30 to top 10 feet. Below that, they start dropping. This is interior borings. Interior boring soils were drier, and the moistures were in the order of about 20%, all the way to a depth of 10 feet. Then it started increasing. Soil suction. We ran the soil suction, and you can see soil suction started from about 3.4. It dropped to about 2.8. Then it goes all the way down about 4. So that means some areas was wet, some areas was dry. It was dry between, like, for a depth of 4 to 6 feet or so. It was kind of wet. Then he went to equilibrium suction. For equilibrium suction, Houston is about 3.4 PF. And you can see the moisture in here. Interior building, moisture of about 20, then kind of gets drops and then jumps up about 10 feet. In terms of water content, these are the borings inside the building. Again, you can see the moisture is all jumping up about 20. The optimal moisture is right here, 17%. Most of these soils were wetter than optimal moisture. Liquidity index shows how wet your soils are, which we showed borings inside the building kind of have positive liquidity index that had water. Borings outside the building was a little drier, but they still were wet. Both of them were wet, but they were just the outside borings were drier than the inside borings. Swell pressures, again, we got a soil sample, we loaded up, we added load to it to get a swell pressure. We measured the swell pressure about 6,000 PSF. That's as high as we got it. Uplift capacity of the drill piers. We put the load on the tip wall panels on piers to see if these piers are going to lift the panels in expansive soil. So we did 2 tests. One, for compressive loading, we loaded the piers and we checked the bearing capacity for a 12-foot pier, 32-inch in diameter, 78 inches, 30 kips, and everything was fine from the loading and all that. We checked for uplift capacity to expansive soils. The expansive soils had a load of about 38.2 kips, but the resistance to skin friction below it was 50.7 kips. So there was not enough. It was not the piers are not going to heave up and lift the panels. Actual panel actually could be more than 30 kips. The typical panels is about 80 kips, so you can use as much as 40 kips load per pier. But when you run this software, it's an FPA developed Foundation Performance Association FPA software. You can get it on the website and check the piers to see a typical pier can lift due to expansive soils. We look at the rainfall data. The construction completed was in or about 2015 or so, and looking at this thing, the rainfall was kind of like about 3.6 inches below it. Before it, then it jumped on the average to higher than that, to about 5.1 inches on the average. So after the construction, there was more moisture that could have helped with edge lift on the north side of the building. However, there was a lot of water due to poor drainage on the north side of the buildings, and we had perch water table. So if you look at the building in here, on the north side, it's heaving in here. And this is the front of the building right there. GPR, it found the steel in the floor slabs. They're supposed to be 18 inches in spacing. That passed. But the steel was a depth of 1.5 to 3 inches below the top of the slab. The spec called for steel at 2.5 inches. So it didn't meet the steel requirement placement. So if you go out there and run GPR, and this is the boring location. If you see the steel in the GPR, reinforcement depth is 3 inches. These are the rebar. This is the concrete core location. Here's another one. We quoted, run GPR, 2.5 to 3 inches of steel below the floor slabs. And they all pass in terms of spacing. The spacing was supposed to be 18 inches. They all pass. But again, here is 1.5 to 2 inches steel depth into the concrete, and the spec called for 2.5 inches. And again, more results of the GPR testing. Steel location is about 2.5 feet. Here's another one. Steel location 1.5 to 2 inches. Concrete floor slab strength. As we discussed with testers, the concrete strength, the all pass. We had one low break in here, 3500 B7, and when we broke the cores. And the ACI 318 has a spec that says, and when you have concrete, the average of the 3 cores should be 85% of the design strength, and no more, and none of the core should drop below 75% of the design strength. So let's say your design strength is 4,000. Lowest number you should get is 3,000. Average of the 3 should be 3,400. And all concrete cores met both these criteria. So they had good concrete on the site. Reasons for the foundation distress. Basically, we think that foundation failed due to inadequate design, poor construction, improper materials, and improper maintenance. Inadequate design. We found out that there was no geotechnical report, and they specify 5 foot of fill under the floor slabs. Our calculations based on a PVR of 3.6 they should have put 8 foot of select fill under the slab to resist to get that PVR to less than 1 inch. Okay, and this floor slab can still move 1.6 inches from the current conditions, when current moisture conditions. So it's already experienced some heave. Poor construction. The spec called for steel placement at 2.5 inches, and we saw basically placement of the steel as low as 1.5 inches. So the steel was not placed at the right location. Improper material. The soil should have a PI of 12 and 20 on the floor slabs, the select fill. And the select fill here is the typical select fill soils with PI between 12 and 20. But we found PIs of almost 29 under the floor slabs. Maintenance. We have poor drainage around the building. You dig right next to the building. There's water. You got the planter areas all mounted with bed liners and area drains that are above the ground, so the water cannot get in there. In summary, we had insufficient select fill underneath the floor slabs of 5 feet. It should have been 8 feet. Poor quality select fill. We had a PI of 29, 28 select fill underneath the floor slabs. The depth of the rebar is supposed to be 2.5 inches. We found them as 1.5 inches shallow. The drainage around the building was poor. So repair techniques, the cheap system, we recommended 2 levels of repairs. One, if you don't want to spend any money, not much money. One, you're going to spend some money. One that you don't want to spend that much money is a level 1. Provide, go out there and fix your planter areas. Make sure you have good drainage out there. Remove the bed liners. Adjust the area drains. And so that's what you do. You just get the water away from the building. Check the drainage design, make sure the gutters are good for a roof system. And so that's the cheap version to improve drainage. And then when you want to spend some more money, we recommend the chemical injections of the floor slabs. You go in there and you do all the drainage improvements, then you go out there, you do chemical injections to a depth of 10 feet and 5 foot away from the building. And you got to go test it 72 hours to make sure all the soils are properly chemical injected. we're not supposed to have more than 1 inches of heave. So despite our recommendations here, of course, some movement can occur. These are typical pictures of chemical injection. These chemicals basically you are used to pre-swell the site before construction or after construction. These are the chemicals that are mixed in here. This is like a low-grade sulfuric acid, and then they're injected into the soil. They do what's called cation exchange. A typical clay particle has got negative charge. You add water to it, positive charge. It absorbs the water and expands. We go out and remove sodium and potassium, put calcium in here, and reduce this basically amount of water that the soil absorbs, therefore reducing the heave. We recommended basically injections to a depth of 10 feet. If you're in Dallas, San Antonio, Austin, we would recommend 15 feet if they have soils. This is a sienna plantation. They're building structures in here pre to construction. We did chemical injections on it. And it basically injected the soil all the way to a depth of 10 feet. This is Brace Heights area. And pre-swell the soils. This is the hole where the chemical injection took place. For this project, we recommended basically drilling holes inside the building. It's a typical hole right there. Its size is a key. And inject to a depth of 10 feet of chemicals, interior of the building. These chemicals react with the soil and reduce the amount of heave that it can experience. These are the holes that need the chemical injection, couple of about 2 foot apart. You go outside and do some chemical injection up to 5 feet from the building. So that was the investigation. So I surely like to see you guys. You have any question and comments? I'm doing a poll in here to see what your thoughts are. I don't know if it's working. Let me see if I can get Vicky in here. Hey, Vicky, will you come here to see if this poll is working? Apparently it's not working. This presentation is on YouTube. You can go out and watch it anytime you want. My email is de@geotecheng.com, 713-699-4000. We got a bunch of upcoming webinars. The poll is not working.
I don't know how to fix this issue. Poll.
No response. You're gonna get PDH hour within a week or so. You got 3 questions here. Looks like it. Huh? He doesn't even show the question and answers, unfortunately. I don't know what your questions are. Send me an email with your questions and I'll respond. There's a problem with the software here. It doesn't show the question and answer. It also doesn't show the polls. I appreciate your time. Send me questions and we'll respond. Thank you very much. Have a good day. Oh, okay. You open the questions in here now. If the bed liners are deep enough in the soil, are they preventing soil water drainage? Would the water not drain through the soil below the liners? Bed liners hold the surface water against the foundation. It causes it to heave. Okay, here's another question. Wouldn't the building code permit mandate written geotech report? A geotech report was done for this project, but we couldn't get a hold of it. Question number 3, it says, I don't think drainage was ever fixed. So somebody was involved in this project. I guess they said there was never any drainage problems. So here's the poll. If you guys are still around, I'm gonna launch the poll.